Hello everyone, my name is Weiting Ma, a postgraduate taught student of chemistry studying in University of Glasgow. Here I'm going to talk about the recent advances in Z-selective alkene metathesis. It is well known that olefins are a very important substance and an important basic raw material in organic synthesis for the production of polyolefins and rubber. Among the many reactions related to olefins, olefin metathesis has been widely used in the pharmaceutical and polymer industries since its discovery. Compared with other reactions, this reaction has less byproducts and waste emissions, and is more environmentally friendly. So what is olefin metathesis reaction? The metathesis reaction of olefins refers to the chemical process in which two parts connected by double bonds in two substrate olefins are exchanged under the action of metal catalysis to form two new olefins. As shown in the figure, the R1 and R2 groups of one olefin are exchanged with the R3 and R4 group of the other olefin. The olefin metathesis reaction is a cyclic reaction. The process is as follows. First, the metal-carbene complex reacts with the olefins to form an intermediate containing the metal heterocyclic butane ring systems. The intermediate was decomposed to obtain a new olefin and a new carbene complex. Then the latter continued to react and the original carbene complex was obtained. There are vacant coordination sites in metal-carbene complex. The whole cycle involves ligand association, 2 plus 2 cycle addition, virtual 2 plus 2 cycle addition, ligand dissociation. The 2005 Nobel Prize in Chemistry was awarded to the chemists Yves Strong, Robert Grubbs, and Richard Schrock for their outstanding contribution to the research and the application of olefin metathesis reactions. Metal-carbene catalysts, Grubbs and Schrock, are the most common catalysts in olefin metathesis reactions. Schrock catalysts usually use molybdenum and tungsten as the central atom. This catalyst has the characteristics of high activity, so it is unstable in air, sensitive to oxygen and water, and expensive. However, there are also related articles showing that a new air-stable Schrock catalyst with 18 electron additions is under development. The Grubbs catalyst uses ruthenium as the central atom and is currently divided into two generations. The first generation is based on the improvement of the Schrock catalyst. The activity of the reaction is low, but it is more stable in air and can be stored at room temperature. The second generation Grubbs catalyst replaces one of the phosphorus ligands with other carbene ligands, which changes the electronic distribution of the central atom, making these catalysts very active but more stable and easier to operate. Compared with the first generation catalyst, the second generation has higher catalytic activity in the reaction, and the reaction time is also reduced accordingly. The first successful example has been demonstrated by molybdenum-based mineral oxide pyrrolide complexes. The researchers divided the ligands into two large and small parts. They chose hexopropylterpene oxide as the large aryl oxide to ensure this ligand is sufficiently large, and they used adamantium as the small imidazole substituent, using the sterol hindrance to achieve Z-selectivity. Different ligand modifications have different effects in stereospecific olefin complexation reactions. For example, the ruthenium catalyst on the left has a biodonated N-heterocyclic carbene moiety, and the right one has a chelate diethylate ligands. These two catalysts show moderate to high Z-activity for reactions of unhindered terminal alkenes. Here is an example of using chiromolybdenum alkyliding catalysis in asymmetric ring opening or closing metathesis. Chiromolybdenum alkyliding complexes containing substitute chiro demonstrated promising capabilities as catalysis for AROM or RCM reaction. Catalytic chiral resolution in asymmetric ring opening or closing metathesis of diene ether was conducted by this catalyst in term and -25 degrees Celsius to afford R dihydrofuran as the product and reacted as diene ether. Ruthenium-based metathesis catalysts with chelating and heterocyclic carbene ligands that catalyze highly Z-selective olefin metathesis. This ruthenium catalyst can maintain high activity at 70 degrees Celsius. In the reaction of alibenzine and cis-1,4-position diacetoxy 2-position butane, able to obtain 90% Z-isomer. This catalyst is among the lowest reported for ruthenium-based olefin metathesis catalysts. More interestingly, the addition of water in the reaction leads to higher conversion and selectivity of Z-type olefin products. Therefore, the dry solvent is unnecessary for the ruthenium catalyst in the olefin metathesis reaction. These features make the catalyst easy to use in common organic and polymer synthesis. Molybdenum catalysts gave excellent Z-selectivity for homocoupling of allyl-trimethylsilane at low conversion. Although the reaction conversion rate is low, the conversion rate can be increased by reducing the reaction pressure, and reducing the pressure will only reduce a small part of the Z-selectivity. For example, when the pressure is only 0.5 mm mercury coulomb, 94% selectivity and 64% conversion rate are formed. Distinctive characteristic of these ruthenium catalysts is that they contain a bidentate NHC with an aryl oxide bridging ligand. This feature translates into a stereogenic metal center and two diastereomeric complexes generated through stereochemical inversion, which can participate in the catalytic cycle. This kind of stereogenic ruthenium carbenes promote efficient ROCM of inner ethers and vinyl sulfide. Transformations are not only exceptionally anti-selective, the versatile products are formed with remarkable high Z-selectivity up to 98%. Here we have a catalyst with a more different central metal atom than common one, which is tungsten. Treatment of reactant with a diacrylamidal, tungsten alkyliding, tungsten catalyst under 1.0 tero of Wickham led to the formation of macrocycle product, a precursor of the anti-cancer natural product ampicillin C, a 97% conversion, 85% yield with high ZAC selectivity, 96%. About ring opening synthesis polymerization, ROMP, which is widely used in industry to produce polymers. To achieve that selective goal, there are several kinds of metal central atoms, such as ruthenium, molybdenum, vanadium, and etc. Here are some examples. The first one, DCMMBD, initiated by molybdenum, esasy-propyl terbium oxide monopyrrolide complexes in toluene, followed by quenching the reaction with benzaldehyde, resulted in formation of over 99% cis-syndiol active poly. The second one, the nitrito-ruthenium complex, ruthenium A, 1 mole%, provided excellent results in ROMP of DCMMBD, yielding poly-DCMMBD in over 95% yield, with 94% cis, in contrast to very low yield 10% with 90% Cs when the catalyst ruthenium B was involved. The third one, cross-metathesis combined ring opening metathesis polymerization (CMOMP) of nonylene with a number of terminal olefins as chain transfer agent at 80 degrees Celsius in the presence of radium catalyst and trimethyl-phosphine, resulted in high-efficient synthesis of N-functionalized polymers, with excellent degree of Z-selectivity, 97 to 98%. Slight decrease in the selectivity was observed if the ROMP was conducted without addition of trimethylphosphine, which is 94%. Nowadays, there are lots of Z-selective catalysts with molybdenum, tungsten, radium, and ruthenium. It is clear that ligand design plays an crucial role for the success. These are all my video essay about. Thanks for watching.